Okay, so maybe we can start. So like Happy New Year, everyone. So last year we had a few talks and tutorials, and uh, and this year, I mean, this is going to be our first talk, and this is by Debjyoti Biswas, who is at IIT Madras. He has been doing some amazing works on quantum error correction, and a nice understanding of. Basically presenting a good understanding of non-Markovian noise and how to deal with that, which is, I mean, one of the challenging models, let's say, of noise, and challenging as well as like a realistic model of noise. So Debjyoti is currently at IIT Madras. He's doing his PhD there, and I mean today he will be talking about his recent work on noise adapted quantum error correction for non-Markovian noise. So Debjyoti, maybe you can like share screen and start the talk. Yeah.
Devjyoti, we can't hear you.
Yeah, I think maybe if you change, I don't know, like you can go near mic and there are different options for microphone and speaker. If you change there, maybe you can see, maybe it's the wrong option has been selected. Like if you can hear us, like can you go near like when on top where there is share mic, camera, like you just click near mic, microphone, and you can select the options maybe.
Can you hear me now?
Yes, it works though.
Yeah,
Perfect. Yeah.
yeah,
So maybe you can screen share and start. Yeah. Okay.
yeah. You can see my screen, right?
I can see it.
Yeah, thanks. Yeah, so thanks, Kishore, for inviting us for this to talk about our quantum error corrections for the non-Markovian noise. And this is the work with Dr. Srikant Utagi and my supervisor Prabha Mandya. And so in this talk, we will take you through the challenges that we or one can face if one attempts to do quantum error corrections for a non-Markovian noise. So there has been some pretty much work in that directions by Daniel Leaders, also recently by Laflamme's group. And 2 years ago, one more paper was there. What they discuss about the challenges that some signatures of the failure of quantum error corrections for the non-Markovian noise. So we take the path of the noise adapted quantum error corrections, not the perfect QEC. So let's start. So I will first take you through the classifications of the noise process and what types of non-Markovinity that we particularly interested in, and then we will talk about the challenges in the quantum error corrections, I mean the perfect quantum error corrections, and how we can, how does approximate quantum error correcting code performs against these kinds of noise process, non-Markovian noise process. So let's start with the noise. We all know that the noise is a source of so noise appears due to the system environment interactions, and it causes the loss of the coherence. And a noise process or the open system dynamics of a system can be represented by a completely positive and a trace preserving map, which essentially generated from a which essentially one can generate from a joint system environment unitary evolutions, which we represented by this unitary matrix V of epsilon, and then we trace out the environmental degrees of freedom, and then this whole process results in a completely positive and trace preserving map. Now, if we start the environment, for example, if we start the environment in a particular state without lots of generality, we can start the environment in the ground states. We have a nice structure in terms of the Krauss operator of the noise that uh, so what do we mean by Markovian and non-Markovian noise? So first of all, a Markovian channel, for a Markovian channel or for a Markovian process where a density matrix of a system is evolving from time t is equal to t0 to t2 will be said to be divisible will be said to be CP divisible if it can be concatenated by such this equality holds. This equality tells you that the system is taken from T0 to T1 by this channel, and then again T1 to T2 by this channel, and it is CP divisible because each and every time interval, say from T2 to from T0 to T1 and T1 to T2, this map is completely positive. But in the non-Markovian case, this intermediate map may not be completely positive or may not even be positive. So the example we will see that it is not even a positive map, meaning it cannot map a positive operator to a positive operator. So how to check that map is a completely positive or not? So just take this map from T1 to T2, and we can calculate the Choi matrix out of that, which can be calculated by these procedures. And if we see the one of the eigenvalues of this Choi matrix is negative, we will say that this map is a non-completely positive. And in that case, the whole map is this divisibility argument breaks down. Uh, it is not CP divisible, but in that case also, the sorry. In that case also, this map, the map from time t1 to t2 can still be a linear map, can still, which implies that it can still preserve the trace of the density matrix, and it can also be hermiticity preserving. That means that a Hermitian operator is get mapped to an Hermitian operator. So these kinds of map, which we call the hermiticity preserving and trace preserving, HPTP map, can be uh, uh, can be decomposed or can be represented by an operator sum difference representations, which means that if you look at this equations one, this fact due to this factor, for some of the indices I, it can be negative. The sign I can take a -1 value. So you can see this this whole map can be decomposed into two parts. One part will be some EI rho EI dagger, and minus some EJ rho EJ dagger. For those values of J, this sign I will take a negative value.
I see.
So
So
yeah.
Debjyoti, like very beautiful like summary.
Mhm.
Like I was thinking like should wouldn't it make more sense to look for this like breakdown of CP condition, or like positivity condition for any of the maps, like let's say ET1 T0. Like why do we want like the ET2 T1, and why don't we, or it does not matter, like I mean, like ET2
It
T1
doesn't
is
matter at
sufficient.
all. T2, T0 to T1, one can look for. We just took an example for that.
I see. So basically, when you
Yeah.
concatenate, if any of the
Mhm.
map is, let's say,
Can
doesn't
be
satisfy the
NCP.
CP or like condition, then
Exactly,
I see. Okay,
Yeah,
okay,
Yeah,
okay.
can
Kishore,
be.
if I jump in
Yeah.
Yeah.
for a couple of points, is that if you notice the map T0 to T1 is still full map.
Mm-hmm.
So it is by definition, because we are considering only 3-point instance.
Mm-hmm.
So T0 to T1 by definition will be CP.
I see. So you
Oh.
construct it such that T0 to T1,
Yes.
you pick
Yeah.
yeah, but then you
Right.
want to go connect T1 to T2, and you say that, let's say if I'm not
Right.
able to find a CP map
Exactly.
to go to the
Exactly.
final destination,
Because
then I see.
T1 is the
Yeah.
point where we assume that system environment state is not a product.
It's an entangled state.
So
Okay, okay, okay.
Yeah.
At T0 it is always a product state. So T0 to T1 will always be a CP map.
That is correct, because the
Yeah.
memory effect has to go beyond T1, right? And
Exactly.
and
Exactly.
so
Exactly.
ET1 T0, yeah, okay,
Yes. And
beautiful,
also
beautiful. Yeah.
to experimentally, I don't think T1 to T2 map is accessible.
Uh,
So T0 to T2 is still a CPTP full map, but
uh-huh,
not
uh-huh.
divisible.
I see.
So it's a
I see.
black box. Basically,
Yes,
T0 to T2 is
exactly.
a black box.
Yeah.
So you don't have the intermediate map that may be NCP for indivisible process, but you don't have access to it.
I see. I see. I
So
see.
a non-Markov dynamics corresponds to a full CPTP map, but need not be divisible.
I see. I see.
Yeah, so that is why the intermediate map
Mhm.
notion comes in. But this can be still extended to multi-time divisibility. And yeah, one can like even go think about even further, like what would be the notions.
So
At least
so
one
so
of the
so let's
intermediate,
say
yeah.
if I say, like, to T3. So let's say it's
Mhm.
T0, T1, T2, T3. So now I have, like, three
Yes,
such maps.
yes,
Now
yes.
T0, T1, T0 is something that I won't care. Like, that is
Right, right,
let's say
right,
same as. Now in
right.
that case, let's say, I mean, if we are thinking about like up to T3, then my any of the map ET2, T1, and
Yes,
ET3, T2
yes.
can break the CP condition.
Exactly, exactly.
Okay.
So
Very nice, very
ultimately, it
nice.
will depend on how your system environment are getting entangled.
Okay, nice, nice.
At that point, it will necessarily be an NCP map because the whole open system theory itself breaks down at that point. So you don't
Hmm.
have a master equation to describe that.
See.
Right. Yeah. So I
Yeah.
think yeah, you can go.
Yeah. Thanks for correcting.
Sorry, so if I can just
Yeah.
clarify something related to that.
Mhm.
So on the definition of a Markovianity, so you
Mhm.
say that this quantum channel E of T2 comma T0 is Markovian if there exists some T1 such that you cannot decompose it into this two CPTP map, or you cannot decompose this for any T1 between this T0 and T2.
Yeah.
Oh,
Mhm.
is it the first one
So
or the
if
second one?
no, so the thing is that if I take the if I say break the time interval from T naught to T2 in two time intervals, so the intermediate time is the T1. So this each and every intervals, this map should be a CP. So that's how we classify this Markovianities.
Oh, okay. So for any
Yeah,
time, for however you
yeah.
break it
Any
into any
arbitrary,
time
yeah.
interval, it should be completely positive. So that's a
Yes, yes,
Markovian.
yes.
Okay. All right. Thanks.
Yeah. Yeah, so going forward, so let's take an example for that. A well-known James Cummings model can be a good example for that. The total Hamiltonian is nothing but something like this, where this sigma z is your atomic state, and it is the AIs or AJs are the bath or the environment's oscillators. So the bath has the spectral density of a Lorentzian form, and where this delta is nothing but the detuning parameters, and this omega naught represents your energy gap between the ground state and the first excited state, and this B is nothing but the spectral bandwidth. So if I take a reduced dynamics. So if I take a unitary out of this total Hamiltonian, which is nothing but the e to the power of minus IHT, and if I do the partial trace over the environmental degrees of freedom, then we will result in channel descriptions of the Krauss operator representations of the system with these two Krauss operator, where this gamma is a time dependent function. It represents the damping strength, or it represents the jumping probability of the system from its excited state to the ground state, or one can say it is the probability of losing a photon, so that the system can make a jump from the higher excited state to the ground state. So in general, this gamma depends upon these two parameters, the gamma naught and the B, which are the gamma naught is nothing but the coupling strength between the system and the environment, and B is nothing but the bandwidth. So it takes this analytical form. This gamma of T depends on this coupling strength and the bandwidth like this. So if I plot this damping strength or the damping probability or the noise strength, whatever we call, for a fixed bandwidth, let's take the bandwidth to be fixed at, for example, 0.1, and if I vary this gamma naught, which is the coupling strength. So if I reduce this gamma naught, you can see that the oscillations in the gamma is kept decreasing, and for a very low couplings, it is monotonically increasing the damping strength. And let's take for this region also, you can see a monotonous behavior of the damping probability. But in these regimes where gamma naught is 5, or one can choose gamma naught to be the 10, one can see that at finite time interval, the noise strength or the damping strength hits 1, which means that the system is going to jump from the higher excited to the higher excited state to the lower excited state, or to the ground state with probability 1. So these are sort of, and after that, since the gamma is kept decreasing, you can see the coherence in the system is reappearing. So these two things are the challenging part for quantum error corrections, because in quantum error corrections we always focus in the low noise regime. We never allow, or we never hit the noise to take 1, the noise strength to take 1, or to allow the system to fail with the probability 1. So how to deal with these two things? One is, it is in the lower time window, it is hitting 1 and it is reappearing the coherence. So one more example one can take, if I fix the gamma naught, the coupling, I can vary the bandwidth, and one can see a monotonous behavior if the bandwidth is too low. So how to deal with this thing in a quantum error corrections? So let's start the quantum error corrections with a very familiar pictures, and you can find these kinds of pictures in the textbook of Nielsen Chong, where we start by doing the encoding. We take a larger Hilbert space and we encode our system or our informations into a subspace of the Hilbert space, and we say that the there should exist a set of errors which should be correctable if and only if those error operator maps this code space to an orthogonal and non-overlapping subspaces which we call the syndrome subspace, and since they are non-overlapping we can detect them faithfully and we can then recover them back to the code space. And these pictures, so for these kinds of codes, they satisfy the well-known non-Laflamme conditions, what we call the QEC conditions. And these conditions demands that there should exist a recovery with something like this, where this unitary is nothing but they appears due to the polar decompositions of this operator EI followed by P. So essentially, what we do is that in quantum error corrections, we breaks any kinds of noise into the Pauli basis, since the Pauli matrix is form a basis. So we can correct the Pauli. In turns, it should correct any general errors. So that's how, if you see any realistic implementations of error correcting protocols, maybe the recent one by Google's or one of the recent paper maybe from envious world of groups, they have implemented the surface code, and we do the Pauli checks, and depending on the syndrome, we revert it back through a Pauli's. But this picture faces a challenge when we these pictures of the syndrome measurements followed by a feedback faces a challenge when we consider the non-Markovian noise. We will come to that, but parallel pictures of the quantum error corrections can be something like that. If we take a code and for some noise operators or for some noise process, the non-Laflamme conditions may not be satisfied exactly, but up to some approximations. So in these pictures, the subspaces may not be orthogonal, may not retain the structures of the code space, and this is a challenging in that. In these pictures, it is a challenging task to extract out the syndrome faithfully and do the recovery. So we ask, what kind of recovery does this Benny-Orshkov conditions or the perturbative Non-Laflamme conditions demands? We will come to this right part later. So let's focus on the perfect QEC part. So recently, the work by Ning-Ping-Kao and the Laflamme, Raymond Laflamme, they proposed that the Non-Laflamme conditions are sufficient to correct any NCP errors. But there is a confusion that we have that, however, they in proving the sufficiency of the Non-Laflamme conditions, they begin with the proof that this lambda ij matrix, this lambda matrix is a Hermitian matrix, and thus it is unitarily diagonalizable. But this is not true in all cases, or it is not true in general. So in a picture where this equality or this hermiticity breaks down, we may not have a standard QEC protocol where we first detect the syndrome and then revert the noise back to the code space depending on the syndrome may fail in a very nice sense. I will come to that in the next slide. So let's consider a NCP map which looks like this, and this is the exact pictures of the operators, some differential representations. That's the significance of this minus sign is due to the this sign I part. So if this is not equal to 0, then it is a NCP. So this leads to the violations of the diagonal part of the or the diagonal form of the Nil-Laflamme conditions, where this diagonal form tells you that any generic kinds of noise can be decomposed in terms of the Pauli's and if you can correct the Pauli's, you can correct those noise. So this thing leads to the violations of these diagonalizations. This is first pointed out by Mark Bayard in 2020. And for example, what is the consequences of these violations is, let's take a very simple example, a bit flip code, a 3-qubit bit flip code, and consider the map, which is nothing but this. But since it is an NCP map, any of this C0 and C1 can take a negative value, but the whole map remains positive, completely positive. But the thing is that when we do a syndrome extractions, that means which qubit got flipped. Sorry. Can you hear me now? I think I got disconnected. Okay, fine. Yeah. So when we extract out the syndrome, that means that which qubit got flipped. What we essentially do mathematically is that we perform a projective measurements onto that subspace. So that if the subspace is if we can define a projector onto the ith syndrome subspace, which is denoted by this pi, we will see that this quantity trace of pi and phi of rho, which is the probability of detections of the ith bit flip, can be negative. So you cannot do the syndrome extractions for this kinds of noise process. So that makes the implementations techniques of QEC impractical. Not the whole QEC impractical, but the implementations techniques. So that implies that we have to think differently in terms of the implementations of the QEC. We may not do the syndrome extractions, but we may take a different route to implement the QEC. We cannot perform the checks first and then do the corrections. There can be a different route. So what we have done is that how does a perfect QEC behave? We just apply this operator, this operator P, which is nothing but the code space projector, and U, which can be a Pauli for a perfect code. Let's take for a 513 code. It can be a set of Paulis directly onto this outcome, and we benchmark the performance of the QEC with the worst case fidelity measurements, which is nothing but we measure the fidelity and take the minima and vary this code vectors, not the code vectors, vary the pure state on the code space so that it can take a minimum value. We take this metric for the merit of our QEC.
Sorry, Debjyoti,
Yeah.
can you explain again? Sorry, maybe I missed it here. So you said that, like because of the breakdown of the non-CP, because the CP condition, which qubit flipped, like you don't get now probability distribution, but it becomes a quasi probability distribution. And due to that, we can't, build a recovery operator to, I mean, at least in the standard setup. To basically do regular static quantum error correction. Now you said that you get this UI. What are these UI that you have?
UI, say for example this code, this UI are nothing but these XNs, the single weight Pauli's or the single weight Pauli X. But my point is that in standard QEC protocol, we follow that the recovery has two parts, right? First, we implement a measurement that cannot hamper the data set. Without hampering the data set, we extract out the syndromes, which we call the syndrome measurements.
Yeah.
And then the recovery part comes through a controlled unitary operations you can implement.
Yeah, through decoder. Yeah.
Yes. So this thing, this trace of PI phi of rho comes in the syndrome measurement part. So if I don't break my QEC into these two things, or if I have a engineering protocol where I can directly implement these Krauss operators, this yeah.
So you are saying that, so normally in, let's say, in the static error correction, let's say, I mean stabilizer
In
code
the
or whatever, like
exactly,
the way we do is that we have this, like we perform these check measurements, and
exactly,
then we send the syndrome data to a decoder, and then the
exactly.
decoder tells us which recovery operator to apply.
Mhm.
Now you are
Exactly.
saying that, like performing this measurement, sending to decoder, and then telling which recovery operator to apply. Everything
Yes.
you combine together, and you are saying that, like, we can get rid of the classical intermediate processing part,
Exactly.
and
Exactly.
just use this particular recovery operator that
Mhm.
you are designing. And in this case, what is you like, what is the I, like, what does I
Uh,
correspond to?
I corresponding to the say for example in the bit flip I corresponding to the ith bit flips.
Uh-huh,
So
uh-huh,
it is just the Pauli operators. I mean, say for example, if the first qubit got flipped,
uh-huh.
what you apply is that XII, right? Identity. X
I
tensor
see.
identity, tensor identity. So UI is nothing but this X tensor identity, something like, yeah. It is uh, those
Sensor
things actually.
identity.
Yeah. So it is a single weight Pauli's in this case. Yeah.
So number of, now, like, number of
Mhm.
such operators that you are applying, this is like, this scales linear with number of qubits, right?
This scales linearly. Yes, exactly.
Right, and
Right.
normally we know that, the decoding is
Mhm.
basically NP hard problem, like, it should so optimal decoding.
Yeah.
So what you are doing, most likely it's not optimal, like, I believe.
Yeah, in that sense, it may not be optimal in terms
I
of
say.
the resource requirements. So if I tell you
Yeah,
the
yeah.
implementations, yeah,
Sure. No. Like there is always this trade-off, right?
yeah,
Things are NP
exactly.
hard, but, like, one has to
Yeah,
anyway continue with life. So yeah. So
yeah.
basically, I see. So you have crafted this recovery operator,
Mhm.
which, you are saying that it get rid of, like, the issue that comes due to NCP of the map. Yeah.
Yes, exactly.
I see. I see.
One maybe the analytical way of constructing this UI is nothing but you take the polar decompositions of this EJP or EIP. It will result in these UIs.
So like, what is the issue with, let's say, normal approximate quantum error correction? Like, you can, there are these optimization based error correction, right? Where you can
Uh,
run these seesaw SDPs, and through that you can
exactly.
find the corresponding, the Choi map
Optimal
corresponding to
recoveries.
yeah, like, corresponding to the, the recovery operator. So like, maybe you looked at how does that recovery operator looks in comparison with your this UI dagger PI.
Yes, we have an example for that. I am
Okay,
coming to
okay,
this.
okay, okay,
In
okay,
just the
I
next
see.
slide, I have this. Yeah.
Okay, I see, I
Yeah.
see. Hmm.
Yeah, so we measured this worst case fidelity for the merit of the performance of the QEC, and let's take the NKD code which satisfies the Nell-Laflamme conditions perfectly for the Pauli noises, and we show that the fidelity loss, which is nothing but this 1 minus f square, takes this form, and this the presence of this sin I or sin L tells you that the fidelity will oscillate in time. So let's take an example, 513 code, where this we constructed this the recovery operator to be something like that, and this UI are nothing but the single weight Pauli operators, and the noise process we considered this the non-Markovian amplitude damping noise, which is adapted to or which is fixed to this regime, where we can have these kinds of oscillations in the fidelity, in the bare qubit fidelity. But with the stabilizer recovery, or stabilizer recovery means these kinds of recovery. With these kinds of recovery, we see that it is also oscillating, and the fidelity. One important part is that the fidelity is going below this 0.5 limit. This 0.5 limit tells you that if the fidelity is 0.5 under some recovery, it tells you that it takes all the noisy subspace and mapped back to the maximally mixed state on the code space. So we will see these kinds of oscillations in the later part of any approximate quantum error correcting protocols also. So this is how a perfect code like the 513 code behaves. We also looked at the CSS code later, but CSS code completely fails. I mean, CSS means particularly we take a look at the 713 code. We can say in that case, one can see that this error corrected fidelity will hit 0 at this time when the information is completely declared. Okay, going forward, let's take the examples of the noise adapted QEC or the approximate QEC. Why
So
noise
you
adapted?
can ask
Yeah.
a question real quick about something in the previous slide. So in your plot here, so just relating that to this fidelity loss eta. So in this case, your MKL matrices will be parameterized with the time t, right? Because
Exactly.
Okay.
Because this operator will have time dependencies, EI and FIs. FIs are the uncorrectable parts.
Right. So you take your non-Markovian amplitude damping channel and you fix like a starting time where you input your code state, right? Like T0 or whatever, then you vary the ending time. Okay.
Yeah, exactly.
So that does that mean like this map is a CP map then? I'm confused.
Yeah, the thing is correct, because what we have done is that we have applied, so here in this slide, we have applied this recovery on this map, right? So the thing is that this map phi is always CP.
Yes, right.
Yeah, so it has a NCP component, but as a whole, it is CP.
I see. Okay. So in its entirety, you still have like this CP map. Okay, I see.
Yes, exactly.
All right, thank you.
So yeah, thanks for the question. Yeah, so in the noise adapted error corrections, one of the nice motivations may be that if I adapt my error correcting protocol to the structures of the noise, we may have to deal with the fewer qubits for encoding a single qubit of informations. For example, the amplitude damping code may be the example for that, where any generic kinds of noise can be corrected, single qubit, any generic kinds of noise can be corrected with at least 5 qubits. That's the Hamming bound tells you. But we can beat this Hamming bound if I adapt my QEC protocol to the amplitude dampings or to the noise process that is dominating in a hardware. Say, for example, in any superconducting hardware, the amplitude damping noise is a dominating noise process. So that we can correct the amplitude damping noise with these code words. This is first pointed out by Debjyoti, and but the problem is that this code doesn't satisfy the Lafleur condition exactly, but it satisfies approximately. From this equation 7, you can see that up to gamma, it is satisfying, but if I include this gamma squared terms also, it doesn't satisfy this code. So when you calculate the fidelity of the error corrections, whatever be the protocol you look for the recovery, the recovery should fall in a gamma squared fashion, 1 minus gamma squared fashion. So a QEC conditions looks like this, are said to be eta correctable if the perturbations is of the order of gamma square, and long recovery, which is proposed by the Debye law, is only possible if this identity holds, and we can correct the noise up to this gamma or approximately with a similar recovery that we have in the perfect QEC conditions, or the perfect QEC conditions tells you. Now, the thing is that if I vary the recovery, I can have a different fidelity, or I can have a better fidelity. So one can construct a better recovery or an optimal recovery through a semi-infinite programming, as first pointed out by Andrews Fletchers in 2007, but it is a numerically hard problem, since if my code length scales, since the search space scales exponentially with the length of the codes. But there exists an analytical way to construct a recovery which is a near optimal recovery, which may not be the optimal, but it's a near optimal, which we call the PETS map. It first pointed out in the information theoretic perspective, and where it says that if we can design a PETS map, something like we can adapt the noise process, and we can design a state specific PETS map which exactly can recover the state from the noise, but it also has a very nice applications in the context of the quantum error corrections, where we can adapt the PETS map or specify the PETS map to a particular code defined by the projector, and we can always adapt this recovery map to the noise process that we are correcting for. So in that sense, it's also called a noise adapted recovery. So the recovery knows what the noise processes are there in your hardware. So depending on that, you tailor your recovery. So again, it follows a similar equality in the quantum error corrections part also. It calls a unital onto the code space, onto the support of your code vectors. And one more thing is that it is not an optimal, it is rather a near optimal recovery. So how near? One can see this paper by Ningman Dam in 2010 and later on 2012. They have quantifications of how near to the optimality in regards to the worst case fidelity measurements these recoveries are. So one more important thing is that it has a good analytical structure, while other recovery may not have this thing. And in Barnum-Mills paper, it was pointed out, I guess, it is an universal recovery channel in the sense that once you know the noise and once you know the code, these structures of the Krauss operators remains as it is. So in that sense, it is universal. So for the Markovian amplitude damping noise, one can see that the bare qubit worst case fidelity falls like this. With the long recovery, the worst case fidelity is something like 1 minus 2.75 gamma square, and with the PETS recovery, it is 1 minus 1.75 gamma square, and it is obviously giving a better protections than the long recoveries. And but how does it tackle non-Markovian errors? So the thing is that since it is a noise adapted recovery, the recovery knows the noise process, so there is a chance that recovery also capture the non-Markovinity of the noise process. In that sense, if the recovery is a non-Markovian recovery, or if the PETS recovery is a non-Markovian PETS recovery, what do I mean by that? I will come to the later slide. What is the meaning of a non-Markovian PETS map, or what is the meaning of a, or in general, what is the quick way to say that whether a recovery or whether a channel is a non-Markovian or not. May not be the based on the CPT visibility, because if you look at the CPT visibility, you have to construct the Choi matrix and then the eigenvalues. But constructing the Choi matrix and calculating the eigenvalue is a tedious work. But we have a in general there exists an algorithm to say what is if the map is non-Markovian or not. So in that sense, we will see this PETS recovery is a non-Markovian. So if I construct a non-Markovian PETS recovery,
By the way, Debjyoti,
yeah,
like let's say, so among different measures, right? If a map
yeah,
is non-Markovian according to a particular metric, uh, will it be like, I mean, can there be like, is there any confusion, like, between different,
measurement.
yeah, different measures of non-Markovianity? Like one measure calls it Markovian, the other calls it non-Markovian. Can it happen, or is it like all measures that we know they agree? I mean.
Yeah, so the thing is that in our case, what the examples that we consider, it invariates under all kinds of measures. But I guess Srikant can tell you more about there is a debate on this,
Yeah.
whether it can be Markovian with respect to some measures and non-Markovian with respect to some other
So,
measures.
so,
So
so indeed,
Srikant.
like, yeah, Srikant, maybe you say, yeah.
yeah. So the quick point is that like uh, measuring is one part and defining it is another. For instance, the strongest form of non-Markovinity you can get is information backflow, and that corresponds to what is called the positive indivisibility of the map. So the intermediate map is not even positive. So that generally corresponds to information backflow. That is known in the literature. And if anything is non-Markov according to P indivisibility, it is non-Markov according to all other measures for sure.
That we know
So
at the moment.
yes, that we
Mhm.
know at the moment. There may be exceptions, but I have not seen.
I see, I see, I see.
So this amplitude damping non-Markov noise is P indivisible, and it has the feature of information backflow. So any measure of non-Markovity should be able to detect, in my understanding, but we don't know.
I see,
And
I
there is
see.
it has single jump operator. I think all of the measures will coincide.
I see. But at the same time, you're saying that we know examples of maps which are
Yeah.
non-Markovian according to a measure, but then
Yes.
another measure say, oh, it's
Yes.
not,
Yes. But
okay, okay.
so that kind
Mm.
of discrepancy goes from bottom to top, not from the bottom, the top from bottom. Like, so what I mean is that the strongest form always will result in all measure detecting it correctly.
Mm-hmm, mm-hmm.
So in
I
only
see.
one case it doesn't. As long as the map is trace preserving, these measures will coincide for a single jump operator. So this information backflow thing will be ineffective in detecting. For instance, trace distance sort of a measure will be ineffective if the map is just CP but not TP. So it will give false signals. But here in our case, the map is CP-TP, but P indivisible. So we are already in the very safe
Yeah.
zone where you can
No.
always
I mean,
guarantee that it's
I just
yeah,
wanted to, like, I mean, for my own
right.
curiosity,
So,
like,
right.
like, can it happen that, yeah,
Yes.
I mean, like what I'm calling non-Markovian, like my reviewer calls
Right.
it Markovian, like,
Yeah, there
yeah,
can be
yeah.
non-Markov processes which do not have information backflow.
I see. Okay.
Yeah, so our PETS recovery map can also be non-Markovian if it is exactly adapted to the noise process. Means that, say for example, our amplitude damping noise with this sort of parameters, if I exactly adapt my recovery to this regime, uh, my recovery will be non-Markovian, and it will have operator some differential representations in that sense. So in that case, the fidelity loss or the infidelity will have something like sin I, sin j form. This sin j comes from this sign, sorry, it should be a double sum. Yeah. So the sin j will come from this j part may come from this noise process, and the I part come from the recovery part. And it is correcting the noise as long as the fidelity loss is less than the bare qubit fidelity loss, or without error correction fidelity loss. But we can as well adapt the bits recovery to the Markov regime of the very same noise process. So in that sense, mathematically what happens, we may not have this sin j or one of the sin I. We will have a single sin I, but still you see the fidelity is oscillating. But in that sense, if I don't adapt it exactly to the noise, what makes the thing difficult is that, or not difficult, it's interesting, is that it is non-unital. And due to this non-unitality, there exists some interesting features. I will come in a minute. So how to calculate this fidelity loss, since we have maximizations, or we have to search for a psi which maximizes this fidelity loss and all, but we have a nicer way of calculating these things. So we take the thing is that any channel, any actions of a channel can be represented by a matrix on the vectors in a Hilbert-Smith space, which is nothing but this matrix element is nothing but this thing, where this O alpha are nothing for a qubit channel are nothing but the Pauli operators. So for example, if I consider an N1 code, which is nothing but I am encoding a single qubit into n qubits, my code space is of dimension 2, then I will have 4 set of such operators, which is one is nothing but this projector, which is similar to the encoded identity operator onto the code space, on the basis of the code space. And look at that, this O1 is nothing but encoded Pauli X, this O3 encoded Pauli Z, and this is Pauli Y. Now, this matrix have a nicer form. It looks like this for a 2-dimensional code space. But for a d-dimensional codes, nothing will change, but the dimensionality of this T matrix will be T minus 1 cross T minus 1. Now, how to calculate the fidelity out of this? So the fidelity, fidelity takes a nicer form, something like this. It is a well-known quadratic form. But if I have a unital channel, that means this phi of P, phi acting on P is the projector, maps back to the P. So unital onto the code space. Then I don't have these tau vectors, and where these R vectors are nothing but the block vectors on the block sphere at the encoded space. So that's how we can simply calculate the fidelity or the infidelity 1 minus f square. Now, why I am looking at this matrix? Because the eigenvalues of this matrix could be a signatures of your P divisibilities. And in turns, that tells you that it can be, the map can be a non-Markovian map. So what we have done is that if I take the derivative, it was first pointed out by Maniscalco and Krusinski. So the signature is that if I take the time derivative of the eigenvalues of this matrix, if it is always less than 0, then the map is said to be a P divisible map. Otherwise, it is not. If it is greater than 0, then it is P indivisible. In that case, we will have the non-Markovity. So we can see here in this plot that for the 4-1 long code and the, say, non-Markovian amplitude damping noise, the lambdas are oscillating in time. So there exists some time, a time where we can see these derivatives as well as the eigenvalues takes a positive value or it is greater than 0. So in that sense, the whole map, the whole recovery is the recovery followed by the noise followed by the recovery is a non-Markov process. And also one can as well see these kinds of behavior for the recovery part itself. You can also verify that these kinds of equality will holds. I mean, there should exist some time after which the lambda will be, the derivative of the lambda will be negative, will be positive, sorry, yeah. So one more interesting aspect of the non-exact adaptations of the noise, which we mean that the PET's recovery is adapted to the Markov regime of the noise, not to the non-Markov regime, but the noise is still a non-Markovian. And you can see that for the 513 code with the PET's recovery, it is a strictly monotonic fall of the worst case fidelity with respect to the damping strength gamma. But for the 4.1 code, which is an approximate code, in the higher gamma regime, around 0.8 or 0.85, the fidelity is increasing, which signature is that I think is that maybe a signature for the information's flow back, but I am not sure about this thing. So these kinds of weird behavior we observed when we adapt to the recovery to the Markovian regime of the noise process. So we also took a different route to correct the non-Markovian amplitude damping through the recovery proposed by Debjyoti. Here also we can construct two varieties of long recovery. One is the Markov long recovery, which is essentially adapted to the Markov regime, and maybe a non-Markov recovery. But we saw that the oscillations are still there in the fidelity. But this performs, performance of this long recovery is not better than the PET's recovery, and it is even worse than the stabilizer error corrections. So the problem with the QEC and these kinds of noise is that it hits for every cases for the both approximate and the general purpose code. In the finite time limit, the noise hits the high noise strength. Noise hits the 1 value, and however but this signifies that if I do that, what we have pointed out earlier is that we cannot do the syndrome extractions or faithful syndrome extractions we cannot do. So why we chose this PET's recovery? Because we don't care about the syndrome extractions in implementing the PETs at all. So maybe one answer to the why optimal recovery, if I look at the optimal recovery by Fletcher, so there is the paper by Fletcher's, if I recall correctly, the channel adapted error corrections of the amplitude damping noise. It is the IEEE paper came out in 2008. There Fletcher and Peter Shore has pointed out an algorithm to extract the syndromes for the 4.1 code. So if I again do the syndrome extractions for the 4.1 code and then apply the recovery operators, as I pointed out earlier, that the syndrome extractions will not result in a positive probabilities. So implementations wise,
No, so sorry, I think in Fletcher case you just optimize for the maps, right? I mean there is no syndrome extraction, right?
Exactly, but I am talking about the implementations techniques. The recovery is perfect. We don't have any problems with the recovery. But yes, I guess I have a plot on that, but not in that slide. I forgot to append that. So in a finite time limit also, if I plot the fidelity for the Fletcher recovery, it will hit the zero fidelity value. So So I'm going to show you some plots. We can get an intuition how does the Fletcher recovery or how does any other recovery apart from the PETS recovery should look like. So in the stabilizer recovery, what we have already seen is that it is an oscillating behavior. But for the non-Markov PETS recovery, you can see saturations of the fidelity near 0.5. It is one of the interesting thing that we notice, but we don't know the physical reason for that. But if I take another route to see whether this PETS recovery is still able to correct the noise in this regime or not, we can look at the recoverability theorem by Mark Wilde.
So Debjyoti, you're saying that,
Yeah.
like, basically to, like to fight non-Markovian errors, use a non-Markovian recovery map.
Recovery map.
Okay.
Yeah.
So
So
and like
yeah.
and your numerics basically shows a gap between what you can do with non-Markovian strategies versus
Markovian
the
strategy.
Markovian strategy that you considered.
Yes, exactly. So why we have considered this Markovian pairs? Because we have an well-established algorithms for implementing those this pairs map on a circuit. But if I look into the non-Markovian pairs, we can still implement in a circuit, in a quantum circuit. But in that case, it will require huge resources. Say for example, for the 4.1 code, it can if I give you the C0 count, it is more than 30,000.
30,000, huh?
Yeah, 30,000 is more. Yeah, it's
Okay,
yeah,
for
yeah.
implementing non-Markovian pairs for 4.1 code.
Yes,
Okay.
exactly. Because in that case, what happens is that you have to construct a joint unitary evolution, something like in my very first slide, I have pointed it out. Uh, this one, you have to construct these kinds of unitaries, and implementing this unitary on a circuit is a hard task, is essentially hard. Yeah,
No,
the number of
but the thing is that, like non-Markovian maps, it seems that so let's say the like, I mean, when as you increase the size of your code, I
Mhm.
believe the gap between non-Markovian strategies and Markovian strategies in terms of the worst case fidelity that they can give you, that will only grow, right? I mean,
that
maybe
yeah,
I'm just guessing. I mean,
yes,
That may
that
not be
can
true.
grow,
So,
but yeah,
Debjyoti, you can show the 7.1 code case.
yeah, that I'm going
Yeah.
to. So this is the thing, the Marco. So we may not have the Markovian pairs, but yeah, for the Markovian pairs, it should be something like saturating at 0.5. So we didn't consider the Markovian pairs here. So for the non-Markovian pairs here, the Markovian pairs, we still see the fidelity is falling at 0.1. So for the 713 code, so that is a problem.
I see.
Yeah, but yes, it's true that. So I also had an idea whether we can approximate the PETS map through a sequence of POVMs for implementing this PETS map on a circuit or
I
not.
mean, I don't know. You
Yeah.
can implement this process tensors, right?
Yeah, process tensors I can implement, but it's resource.
But again, Kishore,
Yeah,
Yeah.
anything with process tensor is also exponentially costly.
I
yeah,
think
yeah,
it won't be.
Yeah. So
yeah.
because you are like implement your
So I know I'm
yeah.
so what I'm worried about is that, let's say, like, like, in our threshold theorem, right? I mean, for
Mhm.
quantum error correction, uh,
Exactly.
if we assume the error model to be correlated, then the threshold can decrease by one or more orders of magnitude.
Okay.
Now let's say unless we are using, like some strategy which is non-Markovian, my worry is that as we scale these quantum devices, I mean, I don't know whether we would be able to, like scale it reliably. Like maybe to fight non-Markovian noise, we will need non-Markovian strategies.
Yeah, that was our confusions also when we are drafting the paper. Um, uh, Srikant was repeatedly asking me that what happens if I consider huge codes, but
Yeah,
yeah.
let's say concatenate it several times and so on. And my worry is that, uh, like it will become maybe bad, like, and maybe the non-Markovian recovery maps is what you need to fight in that case. I
Mhm.
don't know.
Yeah, I
Uh,
guess
Debjyoti, if
yeah.
you, as far as amplitude damping is concerned, if
Mm-hmm.
you look at the 513 code
Mm-hmm.
and Markovian PETS map,
Mm.
you see that the fidelities, we have another you know graph on the paper, but you that the effect of non-unitality will be reduced. So in the long time limit, you can actually see that it's performing as nearly as non-Markov bits.
uh, so,
If
And
so,
so,
you, yeah.
so we have a
so,
small ballpark of 513 code performing better than any other code.
Oh, I guess I have
Yeah.
the,
So you have it. Yeah. So
yeah, this thing,
here's
yeah.
the, yeah. So
So
it's
if
all
I,
Markov
yeah,
bits.
yeah, it's all the Markov bits, and the code is now may not be an approximate, it can be a perfect code. Yeah, one can design the bits map for the short code as well, but I am not sure how well it should perform.
Yeah, hi, Prabha here. Can you hear me?
yeah, hi Prabha.
Yeah.
Yeah,
Hi, sorry,
yeah.
I'm in another event today, and so I'm only mostly silent spectator. But yeah, I think the point that you were making, I think, is a good one. That as the code size increases,
Yeah.
it seems like the Markovian strategy, at least the PET strategy, does worse, and so also the stabilizer
Mhm.
strategies. And Debjyoti, isn't that correct, Srikant? Debjyoti, I mean, that's the
Yeah,
point that Kishore is making. That even with between 5 and 7, you see a degradation of performance.
but yeah, but
Isn't that true?
if
Yeah.
I increase the code, so if I consider the start from the 4.1 thing, so
Yeah.
4.1 works, 4.1 doesn't work better than the 5.13 bits map,
Right.
but it's some sense 4.1 better than the 6.13, but 5.13 is better than the 6.13. And also for the 7.13 code, the
Mm-hmm.
stream code, 5.1 is better. But I am not sure about the shore code because up to some measures of the fidelity, something like the entanglement fidelity,
Mm-hmm.
uh, with some other recovery, something which is similar to the long recovery, maybe in
Mm-hmm.
that paper, I guess Peter Van Look and Safado, Carlos
Mm-hmm.
Safado. In that case, in the Markovian for the Markovian amplitude damping noise, the fidelity falls like 1 minus gamma cube. So, but I am not sure how good it should be in the higher noise strength
Yeah,
regime.
so you're right that shore is a bit special, I think, because
Yeah.
it is the smallest Bacon shore sort of thing, right? The 9.1 is the smallest Bacon shore,
Uh,
and we know that the Bacon shore class can correct amplitude
mhm,
damping noise.
mhm,
So maybe it's worth, okay, that's a good point. So maybe one should actually look at something like Bacon shore, where there's a scaling. At least if
mhm,
you look at Markovian amplitude damping, you expect it to scale well as the
mhm.
size of the code increases, and then you can now ask what happens if you have non-Markovian amplitude
Mm.
damping noise of this kind. That would be,
Yeah.
I think, a very, very fair comparison. Yeah, yeah,
Mhm.
yeah. Thanks.
Yeah. So this is
Also,
the,
Kishore, like I,
yeah.
I,
Yeah, yeah.
I also wanted to make one more point is whether a circuit construction for any indivisible CPTP map is possible or not is my question.
Yeah, I mean, so like I mean, we have
Yeah,
been also thinking about this because recently we asked this question, like because there are these dynamical codes came, right? I mean,
right, right,
flocate codes and so on, and with Andrew and Mile, we asked this question: what is the most general way we can do error correction? And it's like
yeah,
what you can think of is that like nature has this open system which is like not letting my open system to be like behave nicely, so it's a fight of
right,
two open systems.
yeah,
And the most general way you can model it using like say let's say a process tensor. and
mm,
uh,
mm,
and we gave this a strategic code formalism. And yeah, like I mean kind of we are working on something which where we I think we got some inspiration from your work also recently, so I think we might put that in a month or something. So basically, I mean, we have been thinking is it the case that like you definitely need non-Markovian strategies to to have some kind of I mean, you need not have. So let's say here you are doing like single time point error correction, right? It's still, I would say,
Exactly.
static error correction. But think about something like you can do flocate code where you can do intermediate measurements and so on. And in that case, you could have even some adaptive measurements that you could do, and through that you could implement let's say a non-Markovian operation overall by through some classical side channel or something. So I mean, like yeah, still it's hazy, like we couldn't find a single example, like I mean, where adaptivity could help us, like I mean, at least in the dynamic. Maybe Andrew can tell more. Yeah. So yeah, like this is something I mean, I mean, it's fascinating. And I don't know, like
yeah.
I mean, analytically showing like some kind of a rigorous separation would be nice. That ultimately you need like non-Markovian strategies to counter non-Markovian noise. Yeah.
Yeah.
Yeah, like maybe via going to like these
Mm-hmm.
dynamical codes, like you have maybe you might need
Mm-hmm.
to implement dynamical codes, like in that case, at least
Mm-hmm.
here you are not getting to do these intermediate measurements, but in dynamical codes you can do these intermediate measurements. And then along the way, I mean, like
Exactly.
you like
Mm-hmm.
you do all the recovery towards the end, like and like which measurement to perform, you just you make it adaptive based on what you got in the past, so you are fighting the memory effects of the environments by introducing some memory effect in your strategy.
Yeah, so that's what you pointed out in your recent work, the strategic
Strategic
code.
Yeah,
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 yeah, that I can remember.
yeah,
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 yeah.
Also,
yeah.
I have one quick point about process tensor is that uh, whenever you try to sort of get into multi-time business where you do the interventions, the whole uh, Lindblad formalism, breaks down,
Hmm.
right? So it's more like an operational laboratory way of looking at open system rather than the Hamiltonian way of looking at the
That is
open
correct.
system.
Yeah, yeah,
When it comes to physics, like I would really want to know what's happening physically rather than just looking at the statistics. But as far as non-Markov noise is concerned, yes, if you go by the process tensor route, you are
yeah,
like looking at only the statistics, and experimenter is now part of the process. Now you don't know what's happening to the noise, and the structure of noise is not known. So unless you
yeah,
do
yeah,
you do full process tomography, and then again you fall into a category of noise adapted or dynamical regime where you know the noise through process tomography, whether through process tensor or otherwise. So I think yeah, these are all the questions I have. So
yeah. I mean, like we have some work coming out. Like maybe I can give a early like teaser. Like it's
yeah,
we have developed like approximate dynamical codes, and I think
Oh.
yeah. So like for dynamical setting for flocate and all, there is
Mm-hmm.
no approximate. Like all the approximate codes are in the static case. So I
Yeah,
mean,
yeah.
so and then we also thought of like let's try it for some non-Markovian and all. And I think we found a beautiful review by I think Srikant, you and Prabha. I think like just few days ago, like I think maybe 1 week ago or something. Yeah.
Yeah, we have like sort of summarized certain points and
Yeah.
which were missing in literature.
It's
Yeah.
quite nice. Yeah.
Thank you.
Yeah.
Yeah, thanks.
Yeah.
Yeah, so that was the performance of the PETS map. And if I include the long recovery also, you can see it is hitting 0, the both Markov and the non-Markov long. So if I also do the Fletcher recoveries, so it will show some improvement in this regime, but it will rapidly fall after that. So that's what I saw previously, but I didn't include it into that those graphs into our draft. But we saw that it has an improvement in this regime, but falls rapidly after that. So considering all those things, we consider the PETs and the long recoveries, and yeah. So regarding the implementations of that, we have some work on how to implement sub-PETs, and one of that algorithm can be used for implementing the non-Markovian channel, but it is resource inefficient. And in terms of the ancilla, one can use just only one ancilla for implementing Markovian pairs. I don't know for the non-Markovian pairs, and the get depth or the get complexity can be reduced. So that's our recent work, what we have seen. And ultimately, I want to end this thing, whether or not we can approximate a non-Markovian channel with a sequence of 2 outcome POVMs. So quite nice reference for these 2 outcome POVMs implementations may be the Lorenzo Viola work in back 2003 maybe, that one can take a look. Or Victor Albert and Steve Godwin, Yang Xiang has a paper on this single ancillary implementations of recovery map. Yeah.
Wow, like this was a very pedagogical and a very nice presentation. Thanks, Debjyoti. They were like, okay, like people had questions and all along the way and all. I mean, yeah, I mean, like Andrew and me mostly, yeah.
Yeah.
And so, but yeah, like if anybody has any question, please just unmute yourself
Please
and
see and ask.
and ask. Yeah.
Stop sharing. You can see the chat. Uh, it's from yeah.
Okay. So it seems yeah, like people may not have question at the moment. So thanks Debjyoti again, and thanks Prabha and Shrikant, like
Yeah.
for like providing all those insights. Uh, and yeah, I would think maybe if you don't mind sharing the like a disc
Yes. I
the
will share
slides.
the.
Yeah. I
I
mean, if
will
you can,
share the slides.
if you don't mind, maybe you can join the Discord and just share. There is a channel where we add the
Yeah.
slides and
Sure.
all. Maybe you could just add it there so that later I think other could access it and so on. Yeah.
Yeah. Sure.
Yeah.
I will share it.
Okay. So
Yeah, thanks for the invitation, Kishore. Yeah, to
yeah,
present the work and everything. And we look forward to your approximate dynamical recorrection paper as well.
okay. Yeah. Thanks for Thanks a lot. Yeah. Okay. So with that, I think we like we stop the session for today. I have stopped.